Yes. Hey, hey, hey. Welcome back again. And let's continue our backtracking journey. And let's solve problem 39. Combination sum. So what will happen is you will be given candidates, which is a list of which is an array, which will have like values inside it, and you'll be given a target. So and your task is to like tell all the possible numbers which can be taken from the candidates to get the actual target. And the thing is that you can actually reuse elements also. For example, if it was 7 and you had a 1 over here, you could actually write 1 7 times to get the target of 7 also. Yeah. Yeah, that's the thing. So the rules are same number can be chosen unlimited number of times. The two numbers are unique only if the frequency of at least one of the chosen number is different. So there is just a fancy way of telling there should be no duplicates. For example, you have 2 comma 2 comma 3, which will give you the sum of 7. You also have 3 comma 2 comma 2, which will give you the sum of 7. But these both are actually like the complete same. So you should not actually have duplicates in your this one also. And yeah, and yeah, the best way to remove duplicates is to actually sort our candidates. And when you sort our candidates, and like whenever you start a new what you tell recursive call, we'll keep track of the current index we are on also. And we'll and what we'll do is that from the current index we'll go till the end of the array. This will make sure that we will never encounter any duplicate. So yeah, first let's define our backtracking. Yes. So yeah, now what you have to do, you have to go through each candidate and then add it to a number and check if that number is actually equal to the target. So yeah, so what we have to do first, we have to start the backtracking. So first we have to have a container for our answer. So and then after doing everything, our answer will be populated with the result. So yeah, so what we'll do, we'll pass our app. So we'll keep the track of current. We'll keep track of current index, which is actually zero at the beginning. We will keep track of current sum, which is also equal to zero. Yeah, we have to send the answer. There's no, I'm again telling, there's no necessity to actually send the answer, mainly because answer is defined inside combination sum, and backtracking is also defined inside combination sum. But by chance, if you have defined it outside like this, then you actually have to send the answer, like answer array also. But when you're doing over here, there's no need to send, but you'll send it to keep the code more cleaner, like to make it more understandable. And then we'll have a temporary array. So yeah, we'll have the start and IDX. We'll have the current sum. We'll have the answer and the temp. Yeah. So now let's get the base cases out of our way. So what will happen? Like the candidates should be equal to target sum. So by chance, if the candidate like the current sum becomes equal to the target sum, that means we can actually return. But if target sum becomes less than the current sum, or in let's tell it properly, if current sum becomes greater than target sum, that means that we could not actually get a path following the current path. Like we could not get the answer following the current path. So we'll continue. If the current sum becomes greater than target, yeah, that means that you could not actually reach the target from the given path. So we'll directly return. We will not do anything. But if the current sum becomes equal to target, that means that we found an actual path. So we'll take the temp and we'll again make a copy of it. We should always make a copy of temp before appending it to our answer array, because if you don't make a copy and you directly append temp, then the temp will be put by reference, and whenever you modify the temp, the answer will also be modified. That's why you have to always make a copy. Yeah, and append it to our answer. After appending to our answer, you can directly return. And yeah, now what we'll do for each number in range. So we'll go from start index to the length of our current sum, not the current sum, to the length of candidate. So what you have to do, like first get the value. So value is actually equal to candidates at the position number. And if by like now what you have to do, you have to add the value to our current sum or running sum, whatever you can call it. So yeah, after you added the value to the current sum, what you have to do? Start backtracking using the yeah. You can actually use the same values again. The only thing is that you have to not use the start index over here. The start index will actually become equal to number. Yeah, start index will actually become equal to this. And yeah, now what you have to do? After finding a valid path or finding invalid path, what will happen? You have to remove the value from the current sum. And now what will happen is that you will actually have the sum, but the thing which you are missing is actually like updating our temporary variable. So what you have to do? Just append the current number which you're on. Yeah. And after doing everything, temp dot pop. Just pop out the top of the stack. And now what will happen is that yeah, this is the actual backtracking part. After you check for a valid solution, if the valid solution is there, you will directly return. But if it is not there, subtract the value from the current sum and pop out the value from the path variable also, like the path which you are traveling, telling that yeah, we could not reach it, or we have already reached this using this path. Let's check a different path. So let's just try to evaluate it once. Yeah, current sum. Yeah, yeah, this is actually working, and there's no need for us to actually like convert our answer into a set and then add every value inside our what do you tell answer, mainly because we are sorting the answer. Oh, yeah, we have to sort our answer. So like it will work for these cases because the actual inputs are sorted. But as soon as our inputs become unsorted, what will happen is that you will get wrong answer. I don't think you'll get wrong answer. Let's just check it out. You'll not get wrong answer, but it will take more time, I think. Yeah. The thing is, you will actually get the answer, but it will take a lot of time to compute and you'll get TLE. So let's just sort a candidate. Yeah, but let's not sort our candidates and check out if it works. But I'm pretty sure you'll get some TLE or something. Or you'll get like, there will be some error. Okay, it's passing. Let's stop. Let's just sort the candidates and check the time complexity. This is because I think there is like no big test case inside lead code, because this should actually give you a TLE. Yeah. Now, if you see the difference, we'll get to know. The last one was like it's 31%, and this one is like 83%. So yeah, there's no actual necessity to sort the candidates. But if you don't sort, then like let's just check it out. You just have one and one and one, and you actually have like really big number. What is the constraint of target? Yeah, this is the reason. The target is actually just 40. Imagine that the target was like 200 or something, then you would like you would obviously get TLE. But since the target is like very small, why is that? What is my candidate not from 240? Oh, candidates are yeah. That's why they are doing like this. They are telling that you can actually do anything. Yeah, imagine if the okay. Yeah, again given that every integer is distinct, that's the reason it's not passing. Yeah, this should actually take a lot of time to compute, mainly because let's add like many twos so that we'll have a lot of paths, I think. And now let's just check it out. Oh yeah, again they have to be unique. That's the reason they're doing it, I think. Yeah, see, what they're telling is that they're restricting our candidates to like they're restricting the output to like very small value. That's why you're not actually getting TLE. But in actuality, if you don't solve, the time complexity will be very bad. Let's just submit it, and I'll submit it and show again. When you don't solve the actual inputs, okay, that's shocking. Yeah, this is the problem with late code. There are a lot of inconsistencies. Yeah, it is actually not passing very well. But when you solve the candidates, I hope it gets like you get better time now, because if it gets lesser time, I don't know what I'll tell. But actually, you have to sort it so that you don't TLE. And when you're given a lot of numbers, you will actually face TLE. Yeah, this is working faster. And yeah, that's all for it. Thank you for watching. See you.